Hi guys, today we're going to be talking about the Anthropocene. And if you haven't seen the first part of this video or the Holocene part 1 video, I suggest you go watch that. It kind of gives an introduction in terms of what we saw throughout the Holocene in terms of Earth, in terms of climate, in terms of human evolution, in terms of mammal evolution, and leads up to where we're at now in the Anthropocene. So if you don't know what the Anthropocene is exactly, here on this time scale down to the bottom right, we have the Anthropocene as the most recent epoch or epoch in the geologic time scale that is happening right now. And it's thought to have started around the mid-20th century, around 1950, and is still continuing today. But we're going to talk a little bit today about why the Anthropocene is thought to be quite different and a little bit more human influenced than any other time throughout Earth's history. So what we're going to be talking about today includes greenhouse gases, future climate change and consequences, including but not limited to migration, water supply, effects on plants, marine phytoplankton productivity, and more. And then ocean acidification, ocean warming, effects on certain animals that we're already seeing, sea level rise, and positive feedback mechanisms that could really complicate what's already going on. But first, we have greenhouse gases. So in terms of greenhouse gases, I've already explained this in plenty of other videos. I talk more about how greenhouse gases work in terms of blanketing the Earth with this layer that solar radiation doesn't want to escape from in my biogeochemical cycles part 1 video. If you want to check that out, I'll link it up here for you. But basically, we know that greenhouse gases cause the Earth to warm. And what contributes to the increasing concentration of greenhouse gases in the atmosphere is the burning of fossil fuels, clearing forests, agricultural activities, and basically everything that we do as humans. So what we're adding into the atmosphere through these activities includes carbon dioxide or CO2 and CH4 or methane, which are both really potent greenhouse gases. And we're releasing these into the atmosphere, which then pretty much infiltrate any environment on Earth, like the ocean, which the ocean can only take so much before it just starts to become really acidic. And we'll talk about the ramifications of increasing CO2 in the ocean and ocean acidification later on. But what we can see in the graph to the bottom right here is this red upward trending line of atmospheric CO2 concentrations since 1960, around the beginning of the Anthropocene. Then we have this upward trending blue data shown from 1990 to 2010. This is the seawater CO2, so ocean CO2 concentrations. So you can imagine this red line in the atmosphere would be a lot steeper if we didn't have the ocean to absorb a lot of that CO2. So that's kind of helping us right now, but the ocean can only take so much before it becomes oversaturated. And we'll talk about that and those possible ramifications as well. Then this green trending down line is the seawater pH, and a lower pH means more acidic. So those are the current trends going on because of increasing greenhouse gas influx to the atmosphere due to human activities. And all of these trends are contributing to what's called global warming. Global warming is the result of increasing temperatures that is due to the increase in greenhouse gas in the atmosphere. And the increase in greenhouse gas in the atmosphere is not only warming Earth by warming the atmosphere by increasing the amount of solar radiation that gets trapped in our atmosphere, but also as a result, we're warming the ocean. And a warming ocean means warming the water that is in contact with glaciers, meaning more melting of glaciers, more melting of frozen methane hydrates in the ocean, which is something we'll also talk about later. And all of that melting could really cause crazy positive feedback mechanisms, which could exacerbate this warming trend. Now we'll talk about those positive feedback mechanisms at the end. First, I want to talk a little bit about future climate change and the consequences. And the first consequences we'll talk about is migration. As regional climates migrate, or basically regional climates change, and certain places start to have different climate patterns, some warmer, some colder, depending on how the overall global climate and wind patterns and ocean currents and everything is changing. These regional climates are going to be migrating, and this will cause forests to migrate, as we actually have seen many times throughout Earth's history, including what we talked about in the last video. During the retreat of the Younger Dryas glaciers, we saw that forest communities, tree communities started to migrate, and in doing so, many tree communities actually began going extinct, as we see with these brown blobs that actually have no modern analog. And future climate change could lead to similar patterns of migration of forests, and therefore migration migration of animals that live in these forests and so on. And therefore, obviously, if some don't migrate or adapt quickly enough, they will die. But in terms of really affecting us as humans, this migration of climates could really affect our agricultural practices. As climates change in certain areas, you're going to have current farmable land maybe become unfavorable for agricultural practices, and you're going to get some other areas that become favorable. So it's a give and take, but obviously it's going to cause a lot of displacement in terms of farmers, and regions that are able to practice agriculture now are going to have to pick up and move, or just, they won't have anything to farm on and they'll have to change their lifestyle completely. And then animals will also obviously migrate with the migrating conditions and environments, because animals are living in the environments that they're adapted to. And if that environment changes, they need to either move with it or they will die. And humans obviously will have to migrate. We're going to talk later about the real danger that certain coastal communities are in, and the fact that they're going to have to move or they will drown when we talk about sea level change later in this lecture. But even without sea level rise, I already talked about how regions that practice agriculture will have to shift along with the migrating climate conditions that go along with such practices. And so not only will humans be displaced based on sea level rise, but also based on changing climate conditions that just become unfavorable. Which brings me to my next topic, which is water supply. Humans do need water to live, and so do a lot of other things like animals and plants. And I talk about in the last lecture over the Holocene how during the last warm period, the medieval warm period, around 900 years ago, we saw much drier climates in Western North America during this period, which acts as a warning in terms of future climate change. If we continue on this warming trend, we could see climates get much drier in currently dry regions and wetter in currently wet regions. And we don't need that. That's not cool. So what we're going to see is that an increase in warming causes an increase in evaporation. The increase in evaporation in the dry regions causes it to be more dry, and then the wet regions get all of that rain out from the evaporation that occurred in the dry region. That's going to cause these really extreme weather conditions. In terms of the dry conditions, that's going to be really dangerous because we're already seeing major water shortages in the Western US and Africa and other places on the globe, and we just don't need any more threats to our water supply. But it's what we're going to see if we see this continuing warming trend. But it's not just about water. More extreme weather events like floods, droughts, wildfires, and tropical cyclones and hurricanes will cause damage to our farmlands, threatening our food security as well as our water security. So it's not just water, it's also food. It's just all being threatened. But is there good news to this climate trend? Well, that brings us to the effect on plants. What we do know is that plants like CO2. They generally do. And that's because they use it to grow. It's like a food to them. So yeah, they like CO2. They're going to like it to a point. But what they don't like that comes along with the CO2 and the increase in greenhouse gases in the atmosphere is the warming that comes along with it. So yes, they do like the food source of having the extra CO2, but the heat and the drier climate that comes along with it, not so much. Many plants, even without being touched by forest fires, have very specific climatic needs. And if climate changes rapidly, they will either have to migrate to continue to get the climatic conditions that they need, or they will die. And one of the things that we actually see with this specific warming trend throughout Earth's history is that the rate of it is faster than anything really that we've ever seen. So the rate is really what is worrisome when it comes to this particular climate change. And we'll talk more about that later and the effects that that will have on other Earth systems. So next we get to marine phytoplankton and productivity. You might also think that the phyto in the name phytoplankton will cause these guys also to become happy with an increase in CO2, but actually recent data shows that they aren't super happy. What we see is that marine phytoplankton productivity has decreased in recent years due to the effect that global warming has on ocean circulation and upwelling. So what we saw in the previous lecture over the Holocene is that the Younger Dryas could have been caused or partially caused by obstruction of ocean circulation after major climate change had occurred. And we've seen this throughout Earth's history. So it's not odd that climate change is affecting ocean circulation circulation patterns. But what this ocean circulation change is causing is a decrease in upwelling. Upwelling is something where lower, deeper, bottom waters of the ocean at continental margins will come up and basically bring nutrients up to surface waters to feed the phytoplankton at the surface. And these nutrients are really important for these phytoplankton communities. And if that upwelling is not occurring, they're not getting those nutrients, and therefore their productivity will go down, like we've seen in recent decades. But circulation is not the only way that climate change is having an effect on the ocean. Ocean acidification is one major way in which increased CO2 concentrations in the atmosphere are making their way into the ocean and causing it to become more acidic. I talk about ocean acidification in my ocean acidification video. I will link that up here for you if you want to check it out. But basically, the ocean has become 30% more acidic in the past 200 years only. And this causes a suite of really not good effects on ocean chemistry, on ocean life. But I want to talk mainly about calcite organisms, because calcite organisms such as corals can be really important for animal communities in the oceans. So what we see in this map over here to the right is the pink splotches. Those are all coral communities, and these maps show aragonite saturation states, which is kind of a measure of acidity based on if calcite or aragonite, which is also calcium carbonate, can precipitate or not. And so the red here in these maps are areas in which the aragonite saturation state is around 1 or less than 1. And when you get aragonite saturation states less than or equal to 1, calcite precipitating organisms cannot precipitate their calcite. And so what we see is that in 2005, up here on this top map, we have some red, but we also have a lot of blue. So areas where corals can grow, as well as other calcite precipitating organisms. But then we see in the 2030 projection, the red starts to infiltrate the blue areas. And then we see a major infiltration by 2050. And this will cause some major devastation in the coral communities that we see today. And we already have some data showing that coral growth rates in the Great Barrier Reef of Australia declined by 13% from 1990 to 2009. 13% just in that time period. But ocean acidification is not the only way corals are going to be affected by climate change. They're already becoming majorly affected by ocean warming. Ocean warming is what causes corals to bleach. And I'm sure you've all heard this term. Basically, it just means that the symbiotic algae that live within the corals leave the coral when the temperature becomes unfavorably warm for them. And this expulsion of their algae causes the coral to become this white calcite skeleton without its helpful algae. And if those algae don't come back within a certain amount of time, the coral will die. And based on bleaching and ocean acidification, it's estimated that corals will go extinct in the next few decades. And this will cause major mass extinctions of all the ocean life that relies on coral communities. And corals aren't the only ones that secrete a calcite skeleton, and therefore aren't the only ones that rely on ocean chemistry to be at a certain level of pH for them to actually be able to make their skeletons. For example, gastropods, coccolithophores, and forams or foraminifera are also organisms that secrete calcite skeletons or tests that will not be able to do so if acidification continues. But that's not the worst of it. A reduced amount of burial of carbonate skeletons that these guys make will increase the amounts of carbon dioxide in the oceans, causing a positive feedback. That is because if you're not having the burial of that carbon-rich material, you're obviously just going to cause the CO2 or carbon content of the ocean to increase more quickly, exacerbating the effects of climate change and global warming as a whole. And this is what's called a positive feedback. We'll talk more about positive feedback mechanisms later in the lecture. But what about effects on animals? There's a lot of animals already feeling the effects of climate change, but I'm just going to give a couple examples. One example are turtles, and this example could also be applicable to alligators, crocodiles, and some lizards. But basically, turtles are at major risk of going extinct due to mostly or all female populations. What is special about turtles and some other reptiles is that the sex of their babies babies will depend on temperature, meaning the hatchlings during warmer seasons will be mostly or all female. The hatchlings during cooler seasons will be more males. So due to the warming trend, we're seeing a lot more females. And as we can see in just this figure down here, there are some populations that are up to 99% females. And even in the adults already, we're already seeing 87% female populations, 69% female populations. It's just going up and up in terms of females, and they're not going to be able to reproduce if they don't have any males in the future. So we need to combat this warming trend as fast as possible in order to have them to start having male babies. One of the other types of animals I wanted to mention in terms of feeling the effects of climate change are polar bears. Polar bears are already starting to show the effects of climate change in that their weight has decreased 15% in just 3 decades, because obviously they can really only hunt their main food source, seals, on ice, and if there's not ice, they're not really able to do that. The general abundance of polar bears has also gone down, and if we continue to see this warming trend occur at such a fast rate, then they might not be able to keep up with the rate at which climate is changing, and then therefore they'd go extinct. And in terms of other animals, just in general, scientists estimate that around 150 to 200 plant, insect, bird, and mammal species are going extinct every 24 hours. Now, extinctions are normal. Background extinctions happen all the time throughout Earth's history. It's not normal for things not to be going extinct. And I talk about background versus mass extinction in my extinction video. If you want to check that out, I'll link it right here. But basically, this is a greater rate of extinction than we've seen since the vanishing of the dinosaurs 65 million years ago. So it does seem like this is not just background, it is more like a mass extinction rate. What about sea level rise? We know that Earth warming equals ice melting, and ice melting equals sea level rising. And as sea level rises, we're going to see a lot of coastal areas get flooded, and so this is going to displace a lot of humans. But the speed at which glaciers are melting is not only because the atmosphere is warming and their surface is getting more solar radiation, but also because ocean water, like we talked about, is also warming, and this is causing melting of the glaciers from the bottom, the sides, and the top all at once, which is just not good in terms of the rate at which ice is melting and the rate at which sea level is rising. It's estimated that sea level will rise at least 1 meter before 2100, and this will endanger the homes of around 1 billion people, as well as at least 1/3 of the world's crop growing land. So again, earlier I talked about the farmable land migration. Yeah, it's gonna migrate. It's gonna have to, because a lot of it's gonna be flooded. And you might think that 1 meter in the next 80 years is not a lot, but in the meantime, we can expect more extreme storm surges, higher tides, and more flooding. And we can see down here to the bottom right, NOAA made this figure showing that higher sea levels mean higher tides and higher storm surges. So if there's a tsunami, it's going to be worse. If there's a storm, flooding is going to be worse. If there's just high tides, it's going to be worse. And the worst thing about the possible consequences of glaciers melting and sea level rise is positive feedback. So I've talked a lot about positive climate feedback mechanisms and negative climate feedback mechanisms in previous videos, like my biogeochemical cycles videos or my snowball earth video, so you can go check those out. But basically, a negative feedback is something that balances out the current trend. So if it's warming, something will happen that will cause a cooling effect to balance out the warming, whereas positive feedback mechanisms exacerbate the current trend. So if something's warming, that will cause something that will cause an even more warming trend. And positive feedbacks are what we're really worried about, because we do not want to exacerbate any current trend. So we don't want positive feedbacks. That makes climate change too fast and nobody can adapt. Humans, animals, plants, nothing. So what are some examples of positive feedback mechanisms occurring today exacerbating the current warming trend? Well, the classic example that's probably the most worrying is albedo. And albedo is surface reflectivity. And we know that ice is very reflective, which is great for cooling Earth's surface. But when it comes to ice that's melting, you're melting away really highly reflective reflective surfaces, and you're exposing more land surface and ocean surface that is darker and therefore absorbs more solar radiation and reflects a lot less solar radiation, causing increased warming, causing more melting, causing increased warming again. That's the positive loop that we see with ice melting. So Arctic sea ice, which currently doesn't melt entirely during the summer, which is good because we don't want it to melt entirely, or else that positive feedback will really kick in during the time of that dark surface exposure. But it's projected to melt entirely during the summer before the end of the 21st century. And that means that during summers where the ice melts completely, the warming will really exacerbate in the Arctic region, causing a lot more absorption during the summer than reflection, and not allow a lot of ice to come back during the winter, and therefore less reflectivity year-round, and just lowering Earth's albedo as a whole and warming it even further. The second positive feedback mechanism we see going on is evergreen coniferous forests migrating north, replacing tundra. As we replace tundra, we are replacing more reflective or higher albedo surfaces with lower albedo surfaces, causing again a lower albedo of Earth as a whole and more absorption of solar radiation. Similarly, as Greenland ice melts and land is exposed, land has a much lower albedo than ice and will absorb a lot more solar radiation. All three of these examples are having to do with albedo because that is a really scary and real positive feedback that will likely heavily influence the warming trend in the future if we don't try and combat it now. The fourth one we have here is as tundra is replaced and the icy soil and permafrost thaws, we're going to get a huge release of methane. Similar to as marine methane hydrates melt, we're going to get a really extreme influx of methane to the oceans and to the atmosphere. This can be seen in the figure to the right here. Basically, methane stores or methane hydrates, as they melt, we're going to get this release of methane to the oceans and then release of methane to the atmosphere. Methane is actually a much more potent greenhouse gas than CO2 even is. So as this occurs, this is going to cause a crazy positive feedback that will cause even more warming and therefore more melting of the hydrates, and then more warming and then melting and then warming. And you can see the loop there. So it's really important to try and keep this under control. And I don't want to end on this negative conversation of positive feedbacks. Ironically, it's negative even though they're positive feedbacks. But I don't want to end on this, so I want to end with a possible negative feedback. What is really unique about this one instance of climate change over all the other climate change instances that have occurred throughout Earth's history is that humans have the brains to realize what's going on and to fix it. No other organism on Earth is able to do anything about climate change, let alone even realize that it's happening. So the fact that we have this knowledge and have the ability to do something about it can be a negative feedback if we decide to actually do something about it. So the only real question is, will we? That is all I have for you guys today. I know it's kind of a gloomy topic, but I'm having to give this lecture to my students next week, so I figured I would give it to y'all for anybody who wants to get the knowledge that is in the chapter in the book that I'm using to make this lecture. So there you go. If you ever want to know what book I'm using for any of my lectures, it's always in the description down below. And with that, thanks so much again for watching, and I will see you guys next time. Bye.